All right. Well, good morning. There's homework. We're going to go through an example in this lecture, which might help you with the homework. If you're not struggling with the homework, then you should have started it by now, or you should be struggling. I don't know why you are struggling more. So homework 3 is due on the 2nd. That's this Wednesday. And it was to write, you take your little Hamming code that you wrote and turn it into a function that's callable from C. And here's a C framework that would call it. And if you look over on the right, you'll see here's the function prototype, or the little Hamming function. It takes a 32-bit unsigned int value and it returns a 32-bit unsigned int result. And because you know how the calling convention works, you should sort of know where those things are. And it's going to look at your arguments. It's going to convert your argument to a 32-bit integer. And then right down here, embedded in this printf statement, it's going to call this Hamming function, which should be your assembly Hamming function. And you should be good. Folks asked for a template, so I'll put this template up on iLearn a little bit later. I have not put it up this morning because I was doing real work this morning. So here's a little template for it. Nothing too elaborate here, nothing you couldn't have figured out on your own. Here's the little typical start, and here's the typical end. Remember that leave is just the same as if I'd written these two instructions. So I'll try to switch back and forth between leave and these throughout the class. You'll just get used to seeing them both. We need to be able to call this label Hamming. That's where our little code is going to start. It's not start. It's not main because it's not an entry point to a program. So it's just Hamming. And in order for this to be callable, we need to make it global. So we make it global up here. And we want to put our stuff in the text section. And if you have other sections, you can put them in here as well. Just whatever you need. So let's walk through a little bit longer example of some code that we will call from C. So here's a pretty simple example of a C function. Shouldn't be anything here that's in any way confusing to you at all. I take an unsigned int count and an array of unsigned ints called vals, and my job is to find the maximum value in this array. And again, not super complicated stuff. I have a current max, which I set to 0 because unsigned ints. And then I loop from the index 0 up to, but not including the index count. And each time through, I increment index. I check to see if the value in the array is greater than my current max. If it is, I set my current max equal to the value in the array, and that's it. And then when I'm done, I return max. There's nothing in here that should be in any way surprising to any of you. What would this look like in assembly? Well, let's build an assembly function that does the same thing. You should be able to do that by now. So we save the base pointer up here at the top. We restore the base pointer down here at the bottom. Easy stuff. We move the stack pointer into the base pointer so that now our base pointer actually points to the bottom of our stack frame. That's the area on the stack that we have that belongs to us. At the end, we put the base pointer back in the stack pointer. And this is kind of a nice thing to do. So imagine that in here in the body, you do some stuff on the stack. And let's say you align the stack and you push some stuff. Don't necessarily pop all of it. You just mess with the stack and you call routines that mess with the stack. At the end, the stack could be who knows where. And this one instruction will fix it, which is kind of neat, assuming you haven't messed with RBP and that no function that you have called has messed with RBP. Remember, it's a convention. Nothing forces me to save and restore RBP. I do it because I want my program to say fault. But maybe if I could manipulate this in just the right way, I could trick the parent program that's calling me into doing something that I would like it to do. But, you know, that's neither here nor there. I would never be so malicious, etc. So there we go. That's the basic prototype of it. The stack pointer can change throughout the body. The base pointer should not. Then I can restore the stack pointer at the end with that, and then I can fix the base pointer with that. And note the pop comes after the move, right? If I did them the other way around, I'd be in trouble because the stack pointer might be messed up, so I can't just pop it. I need to fix the stack pointer before I pop it. Plenty of stuff. Local variables, we're going to need a couple. In the program, we had two, right? We had our current maximum value, and we had a loop index. So let's have a current maximum value and a loop index. Seems like a good thing to me. Let's use RAX to hold our current maximum value. But we're talking about unsigned ints, and those are 4 bytes. So really, we just need the first 4 bytes of RAX, and we call that EAX. So we'll just use EAX as our max. And you can see up here, we put a 0 in there to initialize our current max to 0. We're going to use ECX as our index counter. And so we set it to 0. There you go. So those are our 2 local variables. Local variables are often either in registers or on the stack. Nothing surprising here. The calling convention tells us some interesting stuff, and I have reproduced it at the bottom down here. So EDI is going to hold the array length, right? It's EDI because it's an unsigned int, it's 4 bytes. RSI is going to hold the pointer to the array. It's R because it's a full pointer. It's 64 bits, 8 bytes. Our return value is an unsigned int, so we're just going to let it be EAX, which conveniently currently holds the max, and then ECX will be our array index. These two come to us from the calling convention. The calling convention tells us the first argument's in RDI, and the second one is in RSI. How do I know that it's 4 bytes versus, I don't. That's information that's not present in the compiled version of the program unless I can infer it by seeing that I'm using EDI or something like that. It just isn't there. Okay, the program has to do the right thing based on what it thinks is there. How do I pass complicated things like structures to a program? I pass them as a pointer. Pointer's 8 bytes. I put it in the register. I'm done. That's just how this stuff is working. So it should be pretty straightforward. All right, so I've initialized my 2 local variables. I know where to find my arguments. I know where my return value goes. I'm ready to go. So I need a loop index in ECX. I need that to run from 0 up to the end of the array. And so I'll need to indicate the top of the loop. And I'm going to do that with this little guy. Notice that there's a period in front of it. The period in front of it makes this a local label. And this is a NASM thing. It's not an assembly general thing. It's a NASM thing. So what this is actually doing is creating a label that is max.loop. And you can imagine I might want to use .top or .loop or .out in a bunch of different places in my code. And this lets me do it. This says this is the loop label that is local to this max label. So it's max.loop. Just a way of avoiding polluting the namespace. And so here's the top of my loop. I'm going to go through the body of it, and I'm going to increment ECX each time through, and I'm going to compare ECX to EDI. What was EDI again? EDI was the array length. So I'm comparing index to count from my original C code. And if I am below, I jump back up to loop. And I use jump below because the jump above and jump below are used for unsigned comparisons. Jump greater than and jump less than are used for signed comparisons. These are unsigned ints. So I'm going to jump if ECX is below the number of things in the array back up to the top of the loop and go through it again. There we go. That's my loop. Nothing complicated there. The one thing that's worth noting is suppose my array is empty. What happens? Well, I just plow right into the body of this loop and do something with the array. That's bad. That could be a bug. Could be an exploitable bug. We don't want that. So we need to check to see if EDI is 0 And if it is, we bypass this whole thing. Let's do that. So here we compare EDI to 0. And if it's equal to 0, we jump to dot out, which is right down here. And that just takes us right out. So we've set the max equal to 0. We see if the count is 0. If it is, we jump down here, return. The return value is in EAX, so we return 0, just like we should, I guess. The maximum value in nothing is 0. Sure, I'm willing to believe that that's a thing you could say. Otherwise, if EDI is not 0, then we go ahead and do the loop. All right, so we've solved what might have been a messy problem by adding a little bit of logic around it. So now we need to just do a comparison. We need to compare the maximum to what's in the array at the position pointed to by ECX. Well, the array is pointed to by RSI. The index into the array is ECX, and each element is 4 bytes long. So I need to look at RSI plus ECX times 4. That sounds like a good use for my effective address calculation. And we can see that over here, val's index greater than max becomes the D word at RSI plus RCX times 4 is greater than EAX. That's what we want to check, right? Because EAX is the current max. This is the current value in the array. So let's put some code in to do that. So now I compare EAX to, and in this case, it dereferences it, right? It's the value stored at the address computed by this little equation, RSI plus RCX times 4. Now, these are R's in here. Why are they R's and not E's? Because I've been using E's down here. Because this is an address. I have to use 64-bit versions of the registers. That's okay because I know the top 32 bits are 0 because of 0 extension, which we talked about last time. All right, so I can compute this address. That gives me the location of the RCX element, and I compare that to EAX. And if EAX is above or equal to what's in the array at that point, then I jump over this little move. So I skip. I just come down here and I increment and go on the loop again. But if EAX, which is our max, is not above or equal, in other words, it's below this value, then I take that value from the array and I move it into EAX. So I set my max equal to that. And that's it. So here's the code that will do that. This will do the same thing as that little max function, but should if we've done it correctly. And it's almost complete. But right now it's not callable because max is private to this piece of code. We need to go ahead and add global max. There we go. Now we can go ahead and assemble this, and you can call it and life is good. I didn't have a section directive in here. That's okay. If I had one, what would it be? Well, let's see. There's just executable code. It would be text. So I can have section text. If I don't have that, I'll get maybe a warning, but it'll put everything in the text section anyway. So there you go. There's my code. I've just built a little program that finds the max of the contents of an array, which I'll posit is a little more complicated than what you're doing for homework. Hopefully this all makes sense to you. Let's put it all together and see how things work. I do point out down here that we could optimize it more. That's for future people to do. Let's talk about calling it from C. How do I do that? Well, I create the C files that I need and I compile them. And GCC-C produces .o files that I can then link together. If you ever built a really big project in C, you've probably done this. You may have done it with a make file, but that's what you're doing. I use extern from within C to reference things that aren't in a particular C module, right? C is a modular programming language where each file is a module. And if I want to reference something outside the module, I have to use extern to do that. Or I use the implicit extern of a function prototype. When I write a function prototype, I'm saying here, this function is going to have this signature, and I promise it somewhere. And by default, those are all extern. In fact, you could put the keyword extern in front of it and it would have no change. There'd be no change in it unless you actually declared the function in the current file, in which case, I don't know what would happen. But it's implicit that when I declare a function prototype, it's extern. Now I need to understand what my arguments and my return values are so I'm able to write the assembly that make use of them correctly, and that's just using the AMD64 calling convention. Then I create the assembly files and assemble them. That gives me more .o files, right? Everything just ends up being a .o file. In my assembly, I can use extern to declare C or maybe other assembly things I need that aren't in that file. And I set up arguments. If I want to call something in C from assembly, I set up the arguments according to the calling convention. And then I just call the function. That's normally going to work. There are other calling conventions that are followed by different programming languages on Linux. But most of those stuff that you use that goes through LLVM or something like that is going to use the AMD64 calling convention, and life will be good. So I then call them. I make sure the symbols I want to export from my assembly are declared global. And then once I'm done with that, I just link everything. Link all my .o files together into an executable or a library or whatever it needs to be, and I'm done. This is it. This is the process. You build some C code, you build some assembly code, you compile or assemble all the pieces, and then you link it together. And they use extern to refer to stuff that's found outside the file. And we don't care where that comes from. So linking can be tricky. Linking is a whole subject in and of itself. We'll talk way more about linking than you may want to at some future point. But if you want the C runtime and you want to link with C, the simplest thing to do is usually just to do this. GCC, we'll put -static in here. We'll figure out how to get rid of that later. 64-bit machine, I want the output to be called hello, and I'm going to put together some .o files. If I wanted to turn that into invoking LD, I have to do all the additional work that GCC does. And this is some of it, but not all of it. I need to put the initialization of the C runtime, some other pieces, link with the standard C library, and then put the finalization in here and wrap all of that around my hello.o in the right way, and that puts it together. If you want to know what really happens, what GCC really does, and you have a couple of hours to spare running down obscure commands, run GCC with the -v switch at the end and have a look at it. It will be either a great education or you'll get a migraine. I don't know which one. Could be both. So here's our test program. We'll just write it in C. I include standard.io.h because we're going to write some stuff with printf. Here's my function prototype for max. It says somewhere someone's going to provide max. It's going to take an unsigned int and an array of unsigned ints and return an unsigned int. And beyond that, I don't know what it does or anything about it. It might come from Fortran. It might come from C, C++. There's tricks to linking C++ and C, but it's not that hard. It might come from anywhere. Could be implemented in Rust. I don't know. But somewhere there's someone providing max. And here's my int main, argc, argv, and I like to show this sometimes just so people don't forget it's here, envp. That's your environment variables. We won't use them. I just like to point out that they're there. So I'm going to define an array of unsigned ints. Look at that, 65, 62, 72 is the highest, 90, 103. 103 is the max. There we go. And I'm going to go ahead and then invoke it. I'm going to call max down here. I'm going to pass it the size of my array, which I will just compute like this. If this looks like a dynamic computation to you, you're wrong. It's actually static. When you look at the compiled code, the compiler can figure this number out and just stick it in here. And so if I add stuff up here, it'll just adjust that. And then I pass the array itself of values. And then I return 0. So I'm going to print out the max, and I'm done. There we go. That's my test harness. And we can then try it out. I can go ahead and I can compile my C code, my C version of the function. and then I could compile and link max test and then run it. I get 103. I can try it with my assembly version, and I can compile it, link it, and test it out and get 103. Hopefully, that all just works. So let's see. I have max C here. I have max ASM here. So let's compile max C. And there we go. I get a max.o compiled today at 9:22 a.m. And let's go ahead and then max test.c, and max.o. We'll just link those two together. Great. Let's give it a try. It's always fun to do these things in real time. 103. Yay, that looks great. So let's go ahead and NASM-F ELF64 max.asm, and I will get a max.o. And I get a different one. So this one up here was fairly small, 1,448 bytes. This one's only 704 bytes, a little smaller, 923. And I can go back up and do my link again. And I can run it again, and I get 103. So life's pretty good. So they work. My little assembly program works. It does the same thing as my C program. It actually wasn't much harder to create than the C program, although you probably know C and don't know assembly that well, so your view may differ. But let's think of some improvements we might make to it. So we never used the stack at all. We never used the stack. So let's throw away that stuff at the beginning and the stuff at the end. Can we do that? Sure we can. What if we called something inside the body here? Well, that thing inside the body that we called, if it were going to use the stack or RBP, it would be responsible for saving those things and restoring them, so it wouldn't matter. The fact that our routine doesn't use the stack means we can throw this stuff away. I mention this because often that's what you'll see when you look at compiled programs. You'll see that they don't have this kind of stuff at the beginning and end. That can make it hard to find functions in code. Finding out where the stupid functions are in your program, that can be hard. And there are reasons why malicious people try to make it harder than it needs to be, perhaps. So there we go. You can get rid of those, and that's good. Now we have a shorter program. Everybody likes shorter programs. Let's apply some more idiomatic assembly. So if I go back and look at this, we're putting 0 in EAX, 0 in ECX, and then checking to see if EDI is 0. You won't see this in assembly. You really just typically will not see this. Because whenever you want to compare something to 0, the way it's traditionally done is to use the test instruction and have the register in here as both operands. What does test do? It performs a bitwise AND of its arguments. So RDI, bitwise AND with RDI will be 0 if and only if RDI is 0. So it doesn't modify any register values. Nothing gets changed here. All this does is set flags. And so test RDI will set the 0 flag exactly when RDI is 0. So instead of that compare RDI to 0, I now have test EDI. That's interesting. Instead of a move 0 into RAX, it's usual to exclusive OR a register with itself. Right? 1 exclusive OR with 1 is 0, and 0 exclusive OR with 0 is 0. So when you XOR something with itself, every bit gets wiped out and it becomes 0. So instead of setting something equal to 0, you exclusive OR a register with itself. Why are we doing this? This seems like it's intentionally insane, right? I mean, this just seems crazy. So when you see this XOR erasure with itself, think setting it to 0. When you see test erasure with itself, think checking to see if it's 0. That's bizarre. But it turns out the reason is these instructions use fewer bytes and they execute faster because they don't have to encode the 0 operand. Okay, and that can take several bytes. Let's take a look at what that looks like on the actual machine. If I said compare RDI with 0, I would get this thing. I would use up 7 bytes. I can't compare RDI with an actual keyword 0. That instruction does not exist on the processor. How do I compare RDI with an actual 8-byte result? I put that 8-byte result in another register and I compare 2 registers. Or I put it in memory and I compare RDI to memory. Those are the only 2 ways to do it. If I just do straight compare RDI and 0, it encodes it this way with 4 bytes. But if I use the test trick, I get down to just 3. And in fact, if I use EDI here instead of RDI, I throw away this prefix byte 48 and I have just 2. And that's pretty neat. Now I can move an 8-byte value into RAX, and here's my 1, 2, 3, 4, 5, 6, 7, 8, or 64-byte 0, or 64-bit 0. And I'm moving it into RAX. And you see that's taking 8, 9, 10 bytes. It's a long instruction. That's crowding out most other things from my speculative execution pipeline. I don't like that. So what if I just said move 0 into EAX? That's better. And I'm going to use the 32-bit extension rule, right? The 0 extend rule, which this will have the same effect as the one above it, right? This is going to set all the bits in RAX to 0 because it 0 extends into the higher 32 bits. So now I got a 4-byte 0, a double word 0, and I don't need that 48 prefix to say I want to use the R registers. And so I ended up with just half as many bytes, 5 bytes. That cut it in half just by changing that R to an E. That's great. In fact, if I hadn't put strict here, the assembler would have done this for me. It would have said, oh, you meant this. What if I just XOR RAX with itself? That gives me 3 bytes. Here's that 48 prefix that indicates I want to use the R versions of the registers. But 0 extension rule. If I modify the low 32 bits, it extends into the high. So if I 0 out the low 32 bits, boom, I end up with just 2 bytes. Just 2 bytes. So huge savings here. That means I can put a lot more stuff in my speculative execution pipeline, have fewer memory fetches, have more code within one page. It's all good, and it's all going to result in better performance. Even though it is really cryptic to look at, that's how it's done. Well, okay, we compiled some C code to do Max. What did it look like? Let's take a look. This is our assembly version put through objdump. And we see that here's our little text section. There's max, max loop, max skip, max out. And there are the instructions we put in. Nothing too surprising there. That's what we put in. We'll notice that it goes from hex 0 up to hex 16. So that would be 16 plus 6, which is 22. With the 0, it's 23. So 23 bytes of program code. Here is what the GCC compiler made of our little max function earlier. And I used -02. So this is an optimized version. If you use -0, you get a lot of stuff on the stack, a lot of local variables that you don't care about. It uses 3 times 16, which is 48, 49, 50, 51 for the 0, 51 bytes total. And we might as well take a look at it and see if we can learn anything from it. We know, because of the calling convention, because it has to follow the calling convention, that EDI is still going to be the length, and RSI is still going to be the array pointer. We notice a couple of things immediately. One is this ridiculous looking in branch 64. That's for branch protection, and it's a no-op. Think of it as a no-op. If I have a protected branch that targets this, then it will cause a processor exception if this instruction isn't here, but I don't have to have that. So we can ignore this. And you'll notice I don't do anything with the stack or with the base pointer. Nothing here, and I don't do anything with them down here. The compiler has worked out that we don't need that stuff, and so it's discarded it, right? The instructions you don't execute run really fast, and so we like to not execute lots of instructions. Let's take a look at, well, before we look at this, let's look at this stuff up here. Test EDI. We already know that's asking the question, is EDI 0? If it is, we jump to 30. Way down here, we zero out EAX, which is our return value, and return. So if the count is 0, we jump down here and return 0. Nothing too complicated there. We had the same kind of logic in our program. What's happening here? I see some load effective addresses and some stuff. So here we are going to load EAX with RDI minus 1. Now, RDI is the pointer to our array, and RDI minus 1, is that right? RDI is the count. Man, I'm just mentioned it up here. RDI is the count. RSI is the pointer to our array. RDI is the count. So this loads the count minus 1 into EAX. Okay, we didn't do that, but sure. And then this takes RSI, adds RAX times 4, and then adds 4. What? What is all this doing? Let's go over here and do the math. So for this instruction, the first load effective address, we see that it sets EAX equal to EDI minus 1. It says RDI, it has to be for it to be a full address, but really we know that it's a count, which is just a low of 4 bytes, so it's EDI. So EX is EDI minus 1. And from this, we know that RCX is going to be RSI plus EDI minus 1, right? Because that's what REX is. So let's substitute it in. Times 4 plus 4. We do a little bit of math, and we find out that's EDI times 4, right? Minus 4 plus 4, so EDI. So it's this. It ultimately sets RCX equal to RSI plus EDI times 4, which is, if you think about it, that's the address just after the end of our array. Suppose our array had one thing in it. So the count, EDI, was 1. We take the start of our array and add 1 times 4 to it. And so we've just skipped over the 4-byte one thing in our array, and we're pointing past the end of our array. So that's kind of weird. Don't know why they're doing that yet, but I'm willing to go along and see if it makes sense later. What's that? So here we have 6 bytes of no-op. Now, we just argued that we should use test and XOR to save bytes, and now we're wasting 6 bytes on a no-op, on a thing that literally does nothing. That seems insane. Assembly, it just seems terrible. Well, the trick behind this, there's a reason for this, and the reason for the no-op here is so that this byte, which just happens to be the top of the loop, and if we look down here, we'll see, sure enough, look at that, jump not equal to 18, and that is right here. And we want that to be aligned on an 8-byte boundary. And it is, because we wasted 6 bytes right here to make it aligned. Why does that matter? It turns out things run a little faster when you align the top of the loop. Do you have to? Absolutely not. We didn't in our code. We could have. We could have put an align statement in there, and the assembler would have done this for us. But that seemed silly, so we didn't do it. But you'll see lots of no-ops in code. The compiler often puts them in there in order to align a byte to an 8-byte boundary. All right, so we can ignore that. It's a no-op. What's happening here? So I go to RSI. What is RSI again? RSI is the pointer to the start of our array. And I take the D word from there, the 4-byte, number, the unsigned int, and I put it in EDX. And then I compare EAX, which is our current max. We sort of figured that out along the way, to EDX. So I'm comparing it to the first thing in the array. And then I do this, C move B. What the heck is C move B? Well, C move B is a conditional move. It combines two things. It combines our test to see if the result of the previous comparison was below, that's what the B is for. And if it was, it does a move, which is what this is for. Conditional move if below. All right, so if the max was below the value in the array, then I move the value in the array into the new max. That's it. Well, that's really kind of neat. This eliminated our branch. When we had this branch to over, and so this eliminated a branch. Eliminating branching logic is a big deal. That makes your program run faster. So that sounds like a good thing. Should we put that in our program? Maybe. We'll come back to that. If we switch our program to using CMoveB, we might save a byte. Right? This is a 3-byte instruction, and it turns out the way we implemented it only used 4 bytes. So I don't know. Comme ça, comme ça. So, right, because we had a branch that took 2 bytes, and then we had the move, which took 2 bytes. So we ended up with 4 bytes, and they had just have 3 here. But eliminating the branch is a big deal because, right, the pipeline is trying to fill with these instructions, and the branch means it can't do that. It doesn't know which branch, whether the branch can be taken or not taken, and that breaks the pipeline. Here, the pipeline can just plow right ahead because the condition is built into the instruction itself, and that can improve performance, especially when you have tight loops in the code. All right. So now what do? We add 4 to RSI. Oh, look at that. RSI isn't just the start of our array. It's really a pointer to the current position in the array. And so we advance it by 4, which is the size of an unsigned int. And so we're just going to keep advancing this by 4 each time. And then we compare RSI to RCX. What was RCX? That was 1 past the end of our array. Ah, it makes sense now. This is the stopping location. And so we check to see if we've run past the end of the array. If we have not, we go back up to 18 and go around again and add 4 to RSI each time. Well, it's different from how we implemented it, but it seems reasonable. Then we're done and we return. The return value is already in EAX, so we're good. We just return. Here's a no-op again to make this branch target 30 be aligned on an 8-byte boundary. I mean, we branched to 30 up here if it was 0. So they could have done a little bit better. They could have set EAX to 0 here, and then they would have just branched onto this return and saved all these bytes, but that's okay. The compiler did a pretty good, decent job of figuring it out. It did things a little differently. It had this funny math here to make it work, but that's okay. It did it, and life's good. Let's make some improvements in our code. So let's go ahead and use the conditional move. So here's the program as it stands right now. Right, we eliminated the stack stuff at the top and the bottom. We replaced the clear and obvious setting to 0 and comparing to 0 with exclusive ORing and testing, because that seems like it's a good idea. And now we have these instructions. And here's our conditional move if below, where we check to see if EAX, a current max, is below the value in the array. And notice what I've done. I stole their idea of taking what's in the array and putting it in a register. Our previous code, we actually had this address check in there twice. And that might mean we go to the cache twice, and that takes longer than just checking a register. So doing this once can save us some cycles. So we'll do that. Then I just compare the max to that, and if the max is below that, then I replace it with the value in the array. Nice little tight code. Eliminated one of the branches. That's good. And the rest of it's the same as it was. So that's kind of neat. you'll notice that I went ahead and used EDX to hold that value. I picked EDX because RDX, the register RDX, is not guaranteed to be preserved across function calls, and so no one's going to care if I mess it up. I would have to save it and restore it. Same for EAX, same for ECX, and so on. I don't have to save and restore those. The caller expects that they might get messed up and should have taken actions to preserve it themselves. Remember, there's a difference between caller saved and callee saved registers. All right. For example, I wouldn't want to use RBX because RBX, B as in boy, is a callee saved register. I could use it. I would just want to push its value up here and then maybe pop its value down here to be sure that that I don't mess with it. There are loop instructions. They're pretty simple. I just say loop and a target, and here's how they work. Whenever I encounter a loop instruction, RCX, and it's always this register, it's always the count register, is decremented. And if the result of that decrementing is not 0, then it branches back to target. If it is 0 after decrementing, then the control will fall through to the next instruction, and no flags ever get set by it. So over here is some example code that uses loop. This is not our program. This is just a little example program. So I put 20 in ECX, which actually puts 20 in RCX because of 0 extension. I then 0 out RDI, again because of 0 extension. Here's the top of my loop. I increment EDI, and then I loop to top. And so what's going to happen? First time in, ECX is 20 and EDI is 0. So I'm going to increment this. Now it's 1. I'm going to hit this. The first thing I do is decrement ECX. Now it's 19. 19 is not 0. So I go up here. I then come through it again. Now it's 18. 18 is not 0. Up here. And I just keep doing this. And if you think about this, I'll run it 20 times because when I come in and it came in the first time and it was 20, I come in the last time and it's 1, I decrement it and I stop. And so then I put 60 in EAX to exit and do a syscall, and there was the return value is going to be an EDI, which in this case is going to be incremented 20 times and be 20. The important thing to remember about the loop instruction is it always decrements. If I set ECX to 0 here and I came into this loop, I would immediately decrement it, making it some huge value because of underflow, and I would go in this loop a ridiculous number of times because of that. I always decrement and then test it for 0. Okay, we can use loop in our program. The trick is RCX is going to be counting backwards. Well, that's okay. For max, for computing the max, it doesn't matter which way I go through the array. I could go through it forward or backward or any way I want to, right? As long as I consider every element, then I'll get the right result. Seems fine, right? I can even do a divide and conquer thing where I break the array in half and I compute the max of each half, and I think the max, crazy things like that, recursive algorithms, what have you. Doesn't matter. So in particular, I can run it backwards, and let's do that. So up here, I 0 out EX just like I did before. That's going to be my return value. But now I take the count and I put it in ECX. So now RCX holds the number of elements in the array. That's good. That's the number of times I want to go through the loop. And so here I enter the loop. And now I need to get the next element out of the array. The array is pointed to by RSI. RCX is the 1-based index into the array, right? Because it starts up here with count. And so this is count times 4, which would be past my array. So I subtract 4. Right? I really want RSI plus RCX minus 1 times 4, but this will work just as well. And I have base, index, stride, and offset or displacement. There we go. So that gives me the correct element of the array. I put it in EDX, compare it, conditionally move it, and then I loop back to the top, and that will decrement ECX, see if it's 0, and so on. So there's my new code. And I was able to do this because I recognized that I could run the loop backwards. Why didn't the compiler do this when it was optimizing it? It didn't know it could run the loop backwards. All it knew was we told it to run the loop forward, and that's what it did. All right, the new program uses just 20 bytes. It's really tiny. We can do one more thing, which I think is worth introducing. We can add a macro. NASM has a nice little macro facility. Here I'm going to percent define value B to be this. Looks very much like a pound define in C. And so I'm going to define it to be that, so that now look here, I can just say value at RCX, and it'll replace B with RCX and put this in. Simple and nice. I don't really want to make much in the way of additional changes to it. This seems like it's good. So what's the point of all this? There are a lot of instructions. I introduced a bunch of new instructions in this, from the conditional move family of instructions, and there are many of them, to the loop family of instructions, and there are many of them. We'll talk about the different versions of loop later on. And to show you that an ordinary algorithm that we started out and we coded in a very straightforward way can end up looking like this. And I don't think that's necessarily obvious. It may seem obvious now if you've followed this really closely. If you've gotten lost along the way, then that's what it looks like. It looks weird. It can start out pretty obvious and then rapidly become difficult to understand. And when you're approaching a brand new piece of assembly that you're trying to understand, you're trying to reverse engineer, you need to think about that process, the process that led to that being created, because that can help you understand what's going on. And it's very easy to make hard to find errors in assembly. Very easy. Okay. I beat the compiler. I produced a shorter program that will actually run really fast. And I did that because I was able to figure out that the loop can run backwards, and the compiler wasn't able to figure that out. That's okay. Writing assembly is way harder than writing in a high-level language. That's why we have high-level languages. But if you really wanted to obfuscate a program, use convoluted assembly, which is what a lot of people do to avoid their programs being reverse engineered. Lots of assembly instructions. Some are documented, some are undocumented. Some exist for very specific cases, like the conditional moves. And you can learn a lot by writing some C code and seeing what the compiler makes of it, right? So if you want to know, I don't know how to get started on this, on writing this thing in assembly, go write some C and see what the compiler makes of it. Okay. The easiest way to create an assembly program is to write in a high-level language and use a compiler. It is. But as you saw, the compiler can do things that are unintuitive, right? It decided that instead of using our index, it was going to advance the pointer instead and look for when the pointer passed the end of the array. Nothing in our original C code said to do that. The compiler figured out it wanted to do that. There are some things you can only do with assembly, and weirdly, you can still have to beat the compiler. And compilers are really good these days. Whew, that was quite a bit. I think this is probably the right place to take a 5-minute break. So let's do that now. We'll take a 5-minute break and be back shortly. piercing. Okay. Let's shift gears and talk about the ELF format. An executable file has to contain all the information necessary for the operating system to run it. So it needs to tell the operating system, I want you to load the following information into memory. It needs to tell it how it wants that done. It needs to tell it what resources it needs, namely, does it need other chunks of memory in order to operate? And there are lots of different ways to do this. The most common formats are the portable executable format on Windows, the mock object on Mac OS. That's from the mock operating system, which was a microkernel. And the executable and linkable format, ELF, on Linux, Unix, Android, pretty much everywhere else. There are many, many others. A.out is actually not just a file name, but it's actually a file format. It's not the file format of an A.out file on a modern system. That's an ELF file. But at one time it was. There's the common object file format from Windows. There's just a ton of them. And you can read about them on Wikipedia. If you are really into that kind of thing, that's fine. But the ones that matter are PE, Mach-O if you're doing Mac OS, and ELF. And of course, we're on Linux, so we're going to talk about ELF. ELF is defined in the header file for ELF, which you can find in user include elf.h. And if you go and take a look, you'll see what looks like the stuff over here on the right. And this is just the beginning of it. It's a very long file. But it defines all the structures and constants and pieces that go into making up an ELF file. You can include this file, and that'll give you all the definitions, and then you could write code to manipulate an ELF file. That'd be fine and dandy. That's how the system does it. But really, you don't want to do that. There are libraries that are already built specifically to let you manipulate what's in an ELF file. And the runtime system doesn't care about a lot of what's in this file. We'll cover that in a bit, but a lot of stuff that's in here, not a lot of it maybe, but some of it just doesn't matter to the runtime system. There's not much explanation in here, right? For example, we see here program header table entry. What's a program header? It's not explained. Processor specific flags. Well, those are defined a little bit later on, but only sort of. So this is a lot of the definition, but not all the pieces you need in order to understand it. The rest of the stuff you need is in the man page for ELF, which is in section 5 of the man pages. So a man 5 ELF, which is man ELF, will produce this, and then you can take a look at what all this various stuff means. So I need to close the door. And the organization of this man page conveniently sort of follows the organization of the header file. And that's great. And so when you look in here, you see a lot of discussion of stuff like what is the ident? The array of bytes specifies how to interpret the file, blah, blah, blah. This tells you what the magic number is and what the different pieces of it are, 7F, ELF, and so on. So that's pretty handy. So armed with these two things, the header file and the man page, you should be able to figure out how that tiny program I gave you at the beginning of class works. All right. I will actually post something about that on the iLearn site. But this is sort of the time to understand how that works. Do you want to know more about ELF? Of course you do. You're burning to learn more about this important file format. So I would recommend the Hello World ELF tutorial. PyELF tools is something we'll be using in this class. It's a Python package. We'll cover that again when we get to Python, so don't worry too much about that. Other major file formats, they have the same stuff, just in a different order in different places. Maybe they have different names for some of the parts. Sometimes they don't allow all the same stuff, like all executables are dynamically linked on the Mac, whereas you don't have to do that on on other platforms. And there are similar utilities on those. Or you can build the GNU utilities, and you can use objdump and so on to look at what's in a Windows file. That's fine. Objconvert exists. It's not necessarily maintained the best, but I mean, the recognition that the same information is present in these files tells me, why can't I just take an ELF file or a PE file and convert it to a ELF file or a PE file? Why can't I do that? Well, sure, you can do that. And if the processor architecture is the same and a lot of other assumptions are present, maybe you can even run the thing, right? It won't work if it's using libraries that aren't present, but you know, you can convert. That's kind of interesting. I like this little site. Someone has taken the time to draw these really pretty diagrams that you cannot see on this slide, explaining what's going on. And so if I go ahead and I click through to, let's say, ELF, that'll take me in here, and it looks like there's nothing, but in reality, there is a really neat diagram explaining all of the contents of the ELF file, and it's kind of neat. And so lots of information in here in a pretty neat form. Most operating systems do things pretty much the same way. There are differences in the conventions used and the language used, but they're all basically stealing ideas from each other. We're sort of circling in on a common way of doing things. And the punchline is that you may be surprised. You're like, well, I'm only learning about x86 and Linux. You may be surprised how much of that will carry over to other processors and to other operating systems. I think it often surprises people, but once you've got this set of stuff in your head, you can sort of figure out where the placeholders are and where things go on a different processor or a different operating system. I didn't talk about a tool at the beginning, so I'm going to introduce it now. And that tool is, again, revisiting objdump. Objdump will let you look at the contents of an ELF file. You can look at the file headers with F, the section headers with H, all the headers, the symbol table, relocate. We'll cover what some of these things are here in a bit. But you know, again, you can dump out these tables and take a look at what's in the file using objdump. And you may have tried objdump on that little program I gave you at the beginning of the class, and with the hex bytes start.hex. And if you did, you may have discovered that objdump is baffled by it. It doesn't understand what's in there. There's another tool you can use to look at ELF files called readelf, and it's specifically built for ELF files. Objdump is not. Objdump uses a special library that understands ELF and PE and a bunch of other formats as well. Readelf is just there to read ELF files, and it's a little better at it than objdump is. Again, there's a man page for it, so you can do man readelf and understand it. Some common options, and they're a little different from the ones from objdump. H is the file headers. Section headers is a capital S. All the headers is E, the symbol table, and relocations. Readelf-D will show you the libraries and the dynamic link information. That's kind of interesting. If you're on Solaris, there's a tool called elfdump, which is basically the same thing. So here I do a readelf-H, that's the file headers, on ls. So this $ open paren, which ls close. You probably seen me do this. That just places it with the path to ls. And here we go. Here's what it looks like. Here's what the ELF header looks like. And if you were to go and look at the man page and the header file, you can sort of follow along. There's the magic bytes, the class, and so on down the line. -S gives you the section headers, and there are 30 in ls, and it shows you where they are. Okay. We'll talk more about sections and segments here in a bit. So readelf is a really neat tool for it. It's very convenient for looking at it. We can take a look at the symbol table that's present in the file. Lots and lots of symbols. You'll see them listed over here. We're going to use a couple of those coming up, but there you go. If you're curious about what all that means, I posted a video on iLearn that talks about string symbols versus program data in way too much detail. It's basically me at a prompt working with redelf and objdump to walk through the content of these tables and understand what's in them. Let's talk about sections and segments. I keep saying section. I mentioned segments. What's going on there? So you've seen sections already because you've seen section text and section data and all that stuff. It's just a linear sequence of stuff, instructions and data, what have you, that can be given the same access rules. Right? And you define the sections when you lay out your program in assembly. So that's the way you logically organize your program into code, readable data, writable data. You do that by defining sections and specifying the access controls for those sections. A segment is a linear sequence of contiguous bytes in memory. So that you can't do. The linker has to do that. If you want to take control of that, you can with a linker script beyond the scope of this class. The linker's job is to figure out program linkage, to figure out, oh, here you're referring to printf. I've got to go find that somewhere and connect the two, link the two together. Or here's part of your program that's referring to a variable in a different part of the program. I have to know where that variable is stored, give it an address, and then connect those two so they're linked together. So the linker links your program. And there are different types of linkages. Static linkage and dynamic linkage are the two big ones. And we'll talk about both of them. But really what it does is it takes your sections you defined and it lays them out in segments. And the segments have, there could be read-only or executable. They have properties, and they are contiguous blocks of memory. And the segments are actually used at runtime. Sections are not. Once your program has been linked, sections are kept in the file or can be kept in the file for reference, but they don't matter. They're not going to be read again unless you specifically want to go read them. All right. At runtime, all the system cares about is here are the segments and how they should be laid out in memory. All right, a section can be present in 0 or more segments. That may be a little weird to you, but we'll see how that works. The section note GNU property is often loaded into multiple segments. It can contain, a segment can contain 0 or more sections. A segment might not have any sections in it. The technical definition for section is it's the smallest unit of an object file that gets relocated or given a virtual memory address by the linker. And that's done when it puts it into a segment. So sections are used to organize parts of your program. They don't have to be loaded into memory at runtime. They don't have to be allocated. We'll see that. But for example, your text section might go into a readable, executable segment. Your data and your read-only data, they might go into a read-only segment. And you might have a read-write segment over here allocated that's for the stack. So that didn't correspond to any section. It's just the stack segment. Okay. If you're thinking about segment registers, like SS and DS and those, you're thinking about the wrong thing. Different uses of the word segment on the platform. Here's an example. Over on the right is our program, and it has 4 sections. So up here, we have a section called Not Home, which we marked No Alloc. And it contains 3 bytes, 10, 11, and 12. So DB is the thing that declares data bytes. I just declare 10, 11, 12 right here. You can do that wherever you want. There's nothing in this section, but it is allocated. So here I have a section called .empty, and I define a constant. Defining a constant doesn't use up any bytes, so really this section has nothing in it. It's literally empty. Here's my program section, section text. It contains a really super complicated piece of code. It takes the return value and puts it in EAX. What's return value? That's down here in the data section. I've got a section for read-only data. It has, I don't know why this is not over here, but there's a label retval. And it's a data double word of val. What is val? It's 22. So this will be 22. So return value, this is a complicated looking mess that just basically returns the value 22. Yay, I guess? I don't know. So return value, this is 22. But we can see it has 4 sections, and they're all a little bit odd. Not home has data, but it's marked don't allocate. Empty is literally empty. Text has some text in it, some program text, and data has a single data byte in it. So let's see what the assembler makes of it. So we put it through the assembler, and after we go through the assembler, we use objdump. We make a wide table of the headers for section.o, and we see this. We see there are 4 sections: not home, empty, text, and data. Well, those were the ones that were in our program, so nothing there should be a surprise. So we said not home was not allocated. So that's the first one here, not home. And you can see it has flags content and read only, but it doesn't have this flag that all the other ones do, which is alloc. Doesn't have the flag alloc, or the flag load for that matter. Empty. What's in empty? Well, empty has size 0. Not home had size 3 because it had 3 bytes in it. Empty has nothing in it. There's nothing in empty. All we did in empty was define a constant, which did not occupy any space. So it's empty. But you notice it has alloc and load, read only, and data defined for it. Here's the program text. We see it's a whopping 7 bytes. And contents, alloc, load, reloc, which we'll talk about quite a bit, read only, and code. This is an executable. So there's executable stuff in here. And then data, which has size 4. And you can see that it's alloc, load, data. There you go. This is the virtual memory address assigned to it. And you see they're all 0 because they haven't been assigned memory addresses yet, because that's what the linker will do. So we need to begin to look at it after a link. But before we do that, let's look at it with readelf. So again, this is post-assembly, pre-linking, and what the heck? What are all these other sections? Well, they're in there. Objdump just didn't bother to show them to us, but readelf did. It goes ahead and shows us that there are all these other pieces. There's this weird null at the start that it shows us. That's fine. It's basically a placeholder. Don't worry about it. Then there's this shared string table, which is a string table. There's stir tab, which is a string table. And there's sim tab, which is a symbol table. And again, I've got a video up on the site that explains these. Relotext is for relocations, and we'll talk about that later on. Okay. And like it says here, I posted a video that explains those 3. And we'll talk about this in the class. Whew. Let's look at the sections after we link. Holy cow. I just said the sections aren't used post-linking, so why did the linker add so many? Well, it added a lot of metadata to our program, information that you might want to use later on, like it added information about the version of GNU, the interpreter to be used, and we'll talk about that later too. It added some notes. It added a hash. It added just a whole bunch of information to the program, a lot of which is not going to end up being used, but it's there in case you wanted to see it. And again, it adds these because sometimes it wants additional information. The linker wants additional information to be loaded into memory. And the way it can trigger that is by allocating a segment and then that section data being loaded into that segment. So we'll notice a couple of things. Empty is gone. Our dot empty section, which was here, there's dot empty right here with size 0. It ain't there no more. It's gone because the linker determined it was empty and it discarded it. Dot text, dot data, and not home are still there. Not home is here, notice, even though it doesn't have an A in this column, meaning it's not marked allocate. But a lot of things aren't marked allocate, so that's fine. Here are the sections. So redelf-L section is actually going to show me the segments. Section is the name of my program. Sorry, this is really confusing. Confused me for a moment. Redelf-L is going to show me my program headers. Program headers are actually segments, and this is the segment table. That's terrible. I should have done something better than that. Don't name your program after one of the concepts you're discussing. So there's the entry point. There are 11 program headers starting at offset 64, and these are segments with a G, segments. So here we go. They don't really have names, right? They just have information about them. They don't need symbolic names. They're going to be mapped into memory. So they have a virtual address. Notice that's not 0 anymore. That's now got an actual virtual address. It has a physical address. We'll answer the question of why there are both here in a bit. It has a size in the file, and it has a size in memory. And the virtual and physical addresses here are the same. The file and memory sizes are the same. But they don't have to be, and there are cases where they might not be. And that's okay. I think one of these, probably this last load, let's see. Yes, 224, 228. So it is possible for the file size and the virtual size to be different for reasons, right? This aligns it on an 8-byte boundary, but there's only this many bytes in the file, so save some file space and then cause the alignment here. And there you go. So there we have that. And then there's flags like read, write, and execute. So 2 of these are executable. This guy is executable, so that must contain our program text. This is executable, so that must be the stack, and it is the stack. All right. And there are alignment flags over here. So we notice that, for example, this guy needed to be aligned. We can look at how the linker mapped the sections into segments by using this instruction. And so here we go. Here are our segments by number. There are 11 of them. And here are the various sections laid out. And so we see that like segment 9 doesn't have any of our sections in it. That's because segment 9 is the stack frame. We didn't write anything to go in the stack, and we shouldn't. It's just allocated. But we'll notice that dynamic occurs twice. Here's our text. Here's our data. Not home is not gone. It's gone. It's not there. Why isn't it there? Well, empty went away because it was empty. Not home went away because it was marked not allocated. And since it was marked no alloc, it didn't get allocated. But it did, in fact, make its way into the file. So it's present in the file right here. It's just not present anywhere in a segment that gets loaded into memory. It's fine. So what about these things that occur more than once? Let's take a look at that dynamic. From the section table, dynamic has a VMA of 3E00 and a length of 1C0. And it's in segments 6 and 10. Segment 6 starts at 3E00, ooh, right there, and has a length of 1C0. Ooh, that's the length of this. So segment 6 is just dynamic. Great. Segment 10 has a VMA of 3DF0, so it starts before this. How far before this? Difference here is hex 10, which is 16, so 16 bytes earlier than this. And it has a length that's a little bit longer than that. It's 210. And So it completely overlaps section 6. So dynamic occurs just once, but because these segments completely overlap, it occurs in both of them. Not in any way confusing. Do you want to understand the linker better? You can read about linker scripts and stuff down here. If you want to understand why this crazy is happening, that's fine. But there you go. You notice that all the section names start with a period. They don't have to. In fact, in the previous class, I made up my own section names that didn't start with a period. And if you're making up your own names, it's a really good idea for them not to start with a period, because the system starts all of the names it allocates with a period. And so if you use a period, you might conflict with an existing section name, and that could get you in trouble. So if you're going to make up your own ones, feel free to, just don't have a period in them. Segment table, so 2 addresses. There's a virtual memory address, I'll just say VMA, and the load memory address, which we will not talk about much in the future because it won't matter. They'll be the same for everything we care about. The load memory address is where the segment should be loaded into memory, and the virtual memory address is the address at runtime. Some systems you have actual addressable physical memory, and then you have virtual memory at runtime. An example is when you're putting a program in ROM. When you put your program in ROM, you need to address into the ROM where this piece goes, but then at runtime, you'll load it from ROM into virtual memory, and it needs to have a virtual memory address, and they can be different in that case. We don't do that, so we won't worry about it. Now, the virtual memory addresses that we see in here, those are effectively just kind of hints. You could think of them as offsets if you like. On platforms like Linux and Windows and Mac, they're going to randomize the addresses and relocate them. So segments have to be effectively relocatable in memory. And we'll talk about how that works. All right. Whew. We have maybe just enough time to get started on procedure linkage. Let's talk about relocations. I keep mentioning relock and relocations. Let's start with what those are. So over here at the right, we have a program. This program prints the value of the stack pointer in binary. That's what it does. So again, a symbol you can look at and understand. It's got a main function, so it's compiled with GCC. It's static. Well, again, we'll see how to fix that later. Global main, extern put s. We're going to use a standard C library routine to print a string. We use put s. And, we do the standard stuff, and we do leave and return at the end. We set bits equal to the number of bits we want to print out, and that's 64. We're going to print out the full 64 bits of the stack pointer. We put the stack pointer in RAX so we can manipulate it without messing it up. And then we go through this loop to write out each of the bits that's present in here. The only thing that might be a little bit weird is right here. I want to convert each bit into an ASCII 0 or 1. And so I just OR it with the ASCII 0, which happens to be an even value. So when there's a 1, I'll get the ASCII 1. Easy stuff. I could have added it, but ORing it is faster. Well, it's not faster. Doesn't matter. There you go. So that will convert it and write it out. And then I write out the stack pointer, and there's a null right there. So I have a null terminated string. And then I made sure my buffer had a terminating 0, and I did that right here at the line that stick a byte 0 at the end of the buffer. And so I can write out the buffer, and I'm good. The buffer lives in this block started by symbol down here, where I reserve bytes. Res-B is reserve bytes equal to the number of bits plus 1. And now the slides will walk through all of that I just told you. So global main, extra input s, there's my fancy loop. Write out the stuff. Here's the BSS section where we reserve 65 bytes. There's a res-W for words and a res-D for double words and so on, but it doesn't matter that much. And we statically link it. Okay. What are the actual addresses of the labels? So what's the address of main, of top, of text, and buffer? What are those addresses? Well, the assembler doesn't know. That's the job of the linker to figure that out. But the assembler does know how many bytes each of these instructions is going to take up, because it's done that part. And so when we have this loop top, it doesn't know the address of top, but it knows how many bytes from here to here, actually from the start of this instruction up to here. And so it can fill that in. And that code could be moved around, right? It doesn't matter what the address is. This just depends on the distance. And the distance doesn't change, so that will work just fine. So the assembler can fill that in for us. What about referencing text? Well, here we load the address of text into RDI. Here we load the address of buffer into RDI, but we don't know those yet. So we need to tell the linker, hey, when you have an address for these, please fill that in here for me. So how do we do that? Well, let's take a look at what happens after assembly. So here's the file after we have assembled it. We'll notice that sure enough, here's that loop instruction, and it put an ED right here. And if you want to count backwards, we start from here, right? EIP, or RIP is always pointing to the next instruction. So that would be FEDCBA 98765432110 FED. So we go right here to address C. And sure enough, this number is the 8-bit 2's complement of that. 8-bit 2's complement of minus 19. Minus 19 in hex, 19 minus 16 is 3, so it's 13. So it's minus 13. This is how you compute the 2's complement, and we wind up with ED, which we have here, and there you go. You can do all the math you want to convince yourself it works, but this is the 8-byte 2's complement value that takes you up here. It's a signed value, so it could branch up here, or it could branch down here, as long as it fits within negative 128 or positive 127 of 1F. It'll work. Some addresses are still unknown. It could not fill in the reference to text or buffer or put S. And so what it did was, look at this, it put zeros in here. And it put 4 of them. So it reserves space for not a full address, right? A full address would be 8 bytes, but just, 4 bytes. These blank spots that need resolution during linking are called relocations. So the linker will actually go and patch the bytes in here with the correct value once it figures out where things should be. That's our hope, at least. If we use readelf with the -r, we can look at the relocations present in the file, and we see there are 1, 2, 3, 4, 5, 6 of them. 1, 2, 3, 4, 5, 6. Sure, makes sense. And we can see some information about them. It turns out these first 4 hex digits tell you a symbol name. This is the type of relocation, symbol value if it matters. And then here is basically what we figured out this would be. So we see 32-bit reference to buffer, text, put S, so on. These are what these are. If you want to know what these relocation types mean, that's in the AMD64 calling convention. Yes, the calling convention actually specifies this. For this one, the value must sign extend to the correct address. In other words, if I give you 4 bytes, I have to be able to sign extend that to an 8-byte address, and that has to be the correct address. For this one, the value is relative to RIP. So I'm giving you an offset relative to RIP. And you see that 2 of these are relative to RIP, and those are the ones that point to put S. The rest of those we expect to sign extend. So we expect them to be within a 4-byte offset of, within a value that fits in 4 bytes, within a, what is that, 2 to the 30, 2 to the 31 byte offset of the, we expect it to be that close to it. There we go. Yeah, I'm saying this terribly. Sorry. So we wrote buffer -1 in the program, and so we'd expect that to be buffer -1. And in fact, buffer's at the start of BSS, so we see BSS -1. There we go. Here we wrote buffer plus 64, and that is in hex 40, so we expect buffer plus 40, and buffer is the only thing in BSS, so it's BSS plus 40. Text is at the start of the data section, so sure enough, that's data plus 0. Buffer is the start of the BSX section, so that's just straight at BSS plus 0. And that accounts for those 4. We'll come back for putS later. We can figure those out. Once we know what they are, and we do know what they are, right? So we've got relocation information in here. And now that we have that, we can begin to fill the values in. So the linker will put these values in here, and here they are. Does that make sense? Do these values matter? Are they what we expect them to be? If we go and look in the symbol table, we'll find text buffer and putS, and we'll find they have these values. And so we can now do the work to figure it out. Buffer's at this address, and so buffer -1 would be, instead of B0, it would be subtracting 1, so that would be AF. And so we'd have this value, 004C22AF, and look at that, there it is in little Indian form, 004C22AF. Same thing for buffer plus 64. What would that look like? That we'd add 4 to this B, C, D, E, F. It would be F0, and there it is, right there. And down here, we have text at the start of the data section. Text has this address, and there it is. And here's a buffer, it has this address, and there it is. Great. So all of those do, in fact, correctly sign extend, because the sign is, they're positive. So this extends to 32 more zeros. They give you the correct address. We didn't talk about putS yet. That's going to require some thought. So putS is relative to RIP. So what does that mean? Well, we have an address for putS, and it's this address right here, 0041-1830. But it's relative to here and here, right? For this instruction, it's relative to 401CB4. 401CB4, that's RIP. That's putS. If I do the subtraction, I wind up with this offset, and that's in fact what I code in here in Little Indian. And I do the same kind of math down here to get that offset. So these are just offsets with respect to RIP. These are actual addresses. Great. So now we understand how all that works. That's how you get your linkage, your static linkage. The program is now linked. It's full of the correct addresses, and we can run it. These are all specific addresses directly coded into the executable. That's not great. Lots of things want to move your code around, right? Especially things like address space layout randomization. It wants to move your code around, and it would be great if it didn't have to patch your code when it did it. It needs to be position independent code. Some instructions require lots of information. We've already seen them: call, move with an address, jumping somewhere. Those all require that you actually have an address. And ideally, you'd like to write position independent code, or PIC, and then generate a position independent executable, or a PI. So you'll see PIC and PI, you'll see them used interchangeably. They mean slightly different things, but no one really cares. Most of the time, PI will be what you'll see when you're using switches for linking and so on. Whew. We can tell GCC that we're not going to write position independent code with no PI, which is don't try to do that because if it can't do it, it'll fail. Or we can just say static. Static has the same effect, right? It tells it include everything in the executable. In that case, the linker can figure everything out. And it can't be position independent because it's hard-coded addresses in it. So we need to tell GCC that. This is not practical in general to do static linkage this way because programs get to be huge. Right? Every program has to have a copy of all the libraries. That's insane. We don't want that. Imagine if every program on your system had to have all the libraries loaded. You'd be out of memory all the time. Ideally, we load the libraries into memory once. And then through the magic of virtual memories, we're able to map them into everyone's address space. And because it's position independent code, they can run wherever we map them. So think on that one for a bit. We'll figure out how that happens later. But for right now, we're concerned with trying to find out how to write position independent code. Wow. So here's some code. And this code will assemble. I can assemble this code, no problem. I didn't tell it static. I didn't tell it NoPy up here. And so, but the assembler is going to go ahead and do its job. It's when I get to linking that my Hola Mundo program is going to fail. And it's going to fail for a couple of reasons. Mainly, it's going to tell me, hey, you've got this relocation of type PC32, right? Remember, that's the relative to the program counter or RIP. You've got this relocation in your program against this putf symbol, but I can't use that when I'm making a Pi object, right? Because that's not relocatable. I'm going to put an absolute offset in here to putS, but I don't know what putS is going to be. It's dynamic. I can't do that. I can't move this code around. And so it offers you a hint. Recompile with -f pi, which tells GCC to go ahead and make a position independent executable that will absolutely 100% not help us in this case because we didn't use GCC to compile C code. We wrote assembly. So the link failed, bad value, and finally collect2, which if you ever run GCC with the -v, you'll see these sorts of things pop up. Well, what's collect2? Something for you to read about. Linking is hard. If you run GCC with -v, you'll come away with the notion that program linkage is hard. Okay. So this is not position independent. How can we make our Hola Mundo program position independent? Well, we got to figure out how to refer to the message, right? Because we want that to be the address of message, and how to refer to putS because we want to refer to that in a library. Dynamic relocations to the rescue. NASM, and this is a NASM thing, works differently on different assemblers. NASM defines a special operator WRT, or with respect to, and this is typically used to reference code from in one segment from another. But on Linux, we can use it to define relocations. Note the warning. Okay, this will be confusing. So, one approach is to define a relocation, right? Those are those 0 bytes that we'll fill in later for a message. When the actual address for message is known, and that can be assigned during linking, the bytes for the operand can be directly overwritten with the correct address. And I can use this structure right here. Message with respect to ... sim, not the double period. And that will cause the assembler to output a relocation record for this guy right here. The symbol needs to be global for this to work, so I define global message up here. The linker will see it, and it'll define a relocation for it. This won't solve our putS problem because we want that to be dynamically linked. Let's take a look at our explicit relocation. Now we have 1, 2, 3, 4, 5, 6, 7, 8 bytes here because we absolutely told the assembler, I have no idea where message is. I want it linked, but I don't know where it is. So create a relocation record for it. The relocation slot occurs. This is offset 4, 5, 6. The relocation record occurs at offset 6, and it's 8 bytes long. And if we look at it, look at the relocations for Ola 2, we'll see that here is the offset 6 for the relocation, and it's a 64-bit full-on address. Okay? And this is telling the system, when you have the value of that address, go put it here. And the symbol is 6, which if you look in the symbol table, that's going to end up being message. And here's the symbol table, and sure enough, symbol 6 is message. All right, that all got connected together. We didn't need 64 bits for the actual address. After it's been linked, we wound up with using 2 of them. Okay, fine. But it does work. Notice that we modified the text section. We modified the program to make this work. And we get warnings from the linker when we do it. We're told relocation against message in a read-only section. Now, let me go back and cover something to be sure it was clear. This relocation will happen at runtime. At runtime, the system will go and patch the binary with the correct value for message. If that seems terrible to you, it's because it's terrible. Who does that? The dynamic linker and so on are responsible for doing that. Don't do that. It's basically saying, don't make me patch a read-only section at runtime. But you know what? I'll just give you a warning this time and let you off, and I'll go ahead and do it. So how can we not do that? All right, we need a better method. Here's where it's going to get a little bit crazy, so buckle up. We're modifying the code, but suppose we don't modify the code. Suppose instead of modifying the code, we have an intermediary that we do modify. So instead of modifying the bytes in the code, let's say that our code points to a table. Here's a table. It points to the table, and the table has pointers to other things we care about. That would be nice, because then we'd modify the table and not modify the code. The way this would work is, instead of moving message into here, I would move a location in the table that corresponded to message into here. So I would say, go get the contents of, in this case, table plus 0, and put the 8 bytes that are there into RDI. Well, what's there? What's here is the address of message. How does it get there? The system defines a relocation for these 8 bytes to point to message. So at runtime, the system patches this table with the correct 8 bytes pointing to message. And that's all it has to do, because I'm already pointing to those. I didn't need a relocation in my code, right? This and the table have been laid out by the linker, so the linker knows how far this is from the table. It knows the distance, and it can compute this and fill it in. And then at runtime, this has to get filled in, and now everything just works seamlessly. So easy, so simple. Keep the table close to the code, and we can just use a 4-byte offset. Shorter code. Everybody wins. And so you might see something like this. I do the table plus 8 to get a value, or maybe I want to jump somewhere. And so I have another entry in the table for that, and I just call the address I got out of the table. That table is called the global offset table, or the GOT. 2 things to recognize about this. This is mostly, what you'll see is mostly going to apply to 32-bit stuff, but the GOT is not gone. It's still there in 64-bit code. And you're like, well, it's not there in Windows. It's in all these other operating systems. It's there. That's how we do it. And we can make things prettier, so you have to think about the global offset table. But for right now, we're going to explain it to you. It's better if you've seen it, because it can be a source of mischief. So the global offset table is a well-known jump table that holds the address of functions that get passed during relocations. We're not going to make it through all of this today, so we'll have to resume it next time. But let's get as far as we can. When the program starts, the dynamic loader will patch the table to fix any remaining dynamic relocation. So a static relocation can be fixed by the linker. Dynamic ones, we have to wait till runtime to see what address we actually get, and then we can fix them. And the dynamic linker does that for us. Since the global offset table has a well-known location, we can get the address of the GOT, and then we can get addresses of our data with respect to the GOT. And that allows us to write position-independent code. And in fact, we can use tricks like using the difference between the address of the GOT and an address of something we want, and then reference that thing with respect to the GOT. It's super simple. So how do we find it? Well, it turns out there's a symbol. If you were to go back to the page where we looked at the symbol table, you would see that one of the symbols was the global offset table. Great. So there we go. It's a symbol. We just say external global offset table, and then we're good, right? Can we use it to get the message? If we know the offset from the GOT to message, then I could take that offset, add it to the base address of the global offset table, and that would give me the complete address of message, which I could then stick in RDI. But how do we get the message offset? Turns out the way to do that is another use of WRT. So again, this is a NASM thing. WRT.GOTOFF computes the distance between the start of the global offset table and the thing that we want. And so that's this distance. If I know the address of the GOT, I add the address of the GOT to this distance, and I know the address of the thing. So easy, so easy. So then I have thing address is thing with respect to GOT-OFF plus the address of the global offset table. My life is good. I'm writing position-independent code. Hooray. How do I find the GOT? I assemble my code. Right, here we go. Here it is. I take the address of the global offset table. I put it in RBX. Now, RBX is a callee saved register. But I'm not a subfunction. I'm the main function, so I'm not going to care. But if I were not, I would save it and store it. And then I'm going to go ahead and take RBX, which is the global offset table address, and add this to it. So I'm going to put it in the register so I have quick access to it. And then I can just do this, and that's going to be great. Congratulations to me. I'm done. I then build my OLA 3 program and immediately get an error. And it tells me ELF64 requires GOT-OFF references to be a Q word. What? What does that even mean? Well, it turns out, that when I do this, I get a double word because it's close enough that I get a double word. And so this is 4 bytes, but this is 8 bytes. And I repeatedly harped on the fact that everything inside these square brackets has to be 64-bit things. This isn't going to work. So boo, that's not going to work. So the solution is to just move that out of the brackets, put it in another register, RDI, and then I can do this. And that works. That works. If you do this and you build it, you will have created a dynamically linked executable. We didn't have to say static up here. You can check it with file. Life is good. We're finished, right? We haven't called putS. We haven't dealt with that yet. We need to deal with the call to putS. We got to figure out how to do that. Can we use the global offset table to get to it? If we can get the linker to create a relocation in the global offset table for putS, then we can get to putS via the GOT. And the way to do that is with another use of WRT, WRT.GOT. We're going to get there eventually, and so now we're there. When this happens, again, 2 periods, it will add a slot to the global offset table for the thing, and it could be the address of a procedure, like putS. It will add a dynamic relocation for the content of the slot in the GOT, and it adds a static relocation to the ELF file for the offset that gets resolved by the linker. All right, so lots of things happen here. But the punchline is I'm going to put a pointer in the GOT, which points to, in our case, put S. So down here is put S. And this is the address of put S. And this is a dynamic relocation. So at runtime, this gets filled in. Okay. And then in my code, I want to be able to refer to that. And the way I do that is I need to know the offset from where I am to this. And I do that with a static one that gets filled in by the linker. So the linker knows this distance. At runtime, we know the address, and then we're good. Whew. Let's do that. How would that look? Well, I just say put S with respect to GOT. That causes it to do all that work for me. I move that offset into R9. I know the address of the GOT is in RBX. So the address of the GOT plus the offset into the GOT of this slot gives me the address of this slot. I go and get the 64 bits that are contained in that slot, which is an address, and I call it. I didn't need to say keyword here because call only takes keywords. And I'm done. I've now called putS through the GOT, and that's awesome. This is a complete dynamically linked Hola Mundo program. It's going to print Hola Mundo. It's didn't have to say static, and there we go. We could have done the same thing for message. We could have said message with respect to .got and would have put a slot in the GOT and put the address in there and all of that, but we didn't need to, right? We could do this too. And there we go. That's our program built using the GOT. Life is awesome. Forever. We still have a problem, but it's one we're not going to discuss until next time. So what I'm going to do next time is go quickly through the introductory slides to the GOT because it's a confusing topic. And then we will resume here where we begin to talk about how the relocations work. And we'll discover that, surprise, we haven't fixed our problem. In fact, the original problem we were trying to solve has come back.